Hi, this is Tzvi Rosen, and this is the second lecture in our series on the history of calculus. And in today's lecture, we're going to stay in ancient Greece and talk about the work of the great Greek mathematician, scientist, inventor, polymath Archimedes. Now, Archimedes was from Syracuse, and he was born around 287 BCE. And died in around 212 BCE. He was Greek mathematician, scientist, and inventor. He reportedly built machines of war to defend Syracuse against Roman invasion. And as a consequence of that invasion, Syracuse was defeated, and the Roman soldiers came looking for him. And as the myth goes, a Roman soldier confronted him in his home as he was sitting drawing geometric figures in the sand, and he yelled at the soldier, "Do not disturb my circles," at which point the soldier killed him. So another great mathematician with an epic death story. Before we get into the mathematics that he did, we'll touch briefly on his scientific achievements. So one famous one is the story of Eureka. This is where Archimedes was tasked with measuring the volume of a crown that the king had, because there was a suspicion that the gold that was given to make the crown was diluted in some way and was not used to make the crown. And so the way that he measured the volume was by submerging the item in water and measuring the displaced water. He was so excited when he found this that he ran naked through the streets after his bath, screaming, "Eureka, I have found it." He also did work on levers, discovering the law of the lever, which relates the distance from the fulcrum to the forces being applied to either side of the lever. And he famously said, "Give me a place to stand on and I will move the earth." He also designed a nifty tool called the Archimedes screw. And this is a device where, as you turn it, water ascends the screw and comes out at the top. So it's a way to, a primitive way to pump water. Okay, and now we can get to his mathematical achievements. And he was famous for applying the method of exhaustion. This was a method which was introduced earlier by Antiphon in 5th century BCE. And the strategy is to measure a region by inscribing a sequence of polygons that comes closer and closer to the true area. This was used by Euclid in his masterwork of early geometry called the Elements. And it was used extensively by Archimedes for the area of an ellipse, for the volume of a sphere, the volume of a cylinder, the area bounded by a spiral, etc., etc. But we'll focus on two other accomplishments that he did with the method of exhaustion, and that's the quadrature of the parabola and his estimation of pi. Okay, we'll start with the quadrature of the parabola. So looking at this image on the right, we see a section of a parabola which is cut off by a line segment. Okay, and the proposition goes as follows. Every segment bounded by a parabola and a chord QQ is equal to 4/3 of the triangle, which has the same base as the segment and equal height. Here, the height of the triangle is determined by identifying the vertex of this parabola. So the point P in this image is the vertex, okay, and specifically that's where the tangent to the parabola is parallel to the segment QQ. Okay, so drawing the tangent to the parabola at the point P, you see that's parallel to the point QQ. So taking the triangle PQR Q. Q, that's equal to the entire, that's equal, sorry, to 3/4 of the parabolic segment. Okay. Before we prove this proposition, let's compute an example using calculus. Let's consider the symmetric segment of a parabola y equals x squared. So let's graph that. So we have y equals x squared. Okay. And we'll consider this line passing across. So this will be y equals c. And this is y equals x squared. And computing this point, these 2 points, we're going to have minus square root of c, sorry, positive, apologies, square root of c, c, and minus square root of c, c. And we want to get this full parabolic segment, but we want to see specifically how this relates to the triangle, this triangle. Okay. And if we call this Q, Q, P, so what is the area of P, Q, Q? Well, this is going to be 1/2 base times height. So that's going to be 1/2 times, the base we'll take to be the top of the triangle. That's twice the square root of c. And the height is c. So the 1/2 and 2 cancel, and we get c to the 3/2. Okay, how about the green region? Well, we know that the area between 2 curves is given by the top function minus the bottom function integrated over the interval. So the parabolic area is going to be equal to the integral from minus root c to positive root c of c minus x squared dx. Okay, so that's going to be, using standard power rule, cx minus x cubed over 3, where x goes from minus root c to root c. Okay, plugging that in, we have c to the 3/2 minus c to the 3/2 over 3 minus negative c to the 3/2 minus, so then this is a positive cube, so it's plus c to the 3/2 over 3. So putting it all together, we have 2c to the 3/2 minus 2/3. That gives us 4/3 c to the 3/2. So indeed, this parabolic area is 4/3 of the triangle. So the parabolic area equals 4/3 the triangle PQQ, exactly as the proposition predicted. Okay? So hopefully that convinces you a bit that this might be correct. And the proof goes as follows. And as we discuss this proof, I want you to keep in mind, this is of course about the history of the calculus. So what aspects of this remind you of standard integration, computing areas using integration. And in what ways is this proof different? Okay, so the first step of the proof is to show that the inscribed triangle of half a parabolic segment has 1/8 the area of the inscribed triangle for the full parabolic segment. Okay, so meaning we'll see this in more detail, but in particular, if you have a parabolic segment, okay, and you specify the vertex in the correct way so that its tangent is parallel to the line segment. So this triangle, this blue triangle, will be 8 times the triangle that you get if you just look at the segment to either the left or the right of that vertex. Okay. Second, we'll argue that each tier, meaning as you step down in the area by 1/8, each tier has 2 to the n triangles of area 1/8 to the n times a, where a is the original triangle area. So the total area will be 1/4 to the n times a. And finally, so adding up the areas 1/4 to the n times a for n equal to 0, 1, 2, etc., we will then argue that the sum 1 plus 1/4 plus 1/4 squared, etc., is equal to 4/3. And that allows us to conclude that the parabolic segment has area 4/3 of the triangle. Let's start by showing that the inscribed triangle in half the parabolic segment will be 1/8 of the area of the inscribed triangle in the full segment. So let's label some points here. We're going to call this P. This will be Q. This can be little q. We're going to call this R. This is the midpoint between Q and little q, so that'll be V. This is the midpoint between Q and V, that'll be M. Okay, the line parallel to PV passing through M goes through R and the parabola. Where it hits the parabola is R. It hits the other line, we'll call that X, and this will be Y. So what we want to show is that the triangle PQQ is equal to 8 times the triangle PQR. Okay. So the first thing we want to do here is observe what the length of Rx is relative to the full segment XM. So there's a property of parabolas that, and this is kind of related to the equation y equals x squared, that the ratio the ratio mx to rx will be equal to the ratio let's go with the longer first, so it'll be qv squared to mv squared. Okay. So what this tells us in our context is that mx is going to be equal to 4 times rx. Okay, because since m is the midpoint of the segment qv, the ratio qv squared to mv squared is 4 to 1. So that tells us that mx is 4 times rx. And in particular, because y is the midpoint of the segment MX, this tells us that RX is equal to RY, and MY is equal to twice RX, or RY. Okay. So that's to start. And we're going to use that fact to analyze these triangles PQQ and PQR. So first of all, we'll observe that PRY and PYM are related to each other since the edges RY and YM are on the same line, and so that means the heights of the triangles will be the same, and just the bases are in proportion. So the triangle PRY times 2 will be equal to the area of the triangle PYM. Okay, again, that's because YM is twice as long as RY. The same argument tells us that twice the area of the triangle QRY is equal to the area of the triangle QYM. Okay, and what that tells us, if we put together the two triangles PRY and QRY, we get, and basically just adding these equations, we get that twice the triangle PQR is equal to the triangle PQM. Okay. Well, the triangle PQM, so this, the edge QM is on the same line and with the same length as the edge MV. So that tells us that, so what we can say about PQM is that PQV has area twice PQM. Okay, and by the same token, it's the triangle PQ little q has 4 times the area of the triangle PQM. Okay, so plugging in this equation, I wanted that to be squiggly, into this last equation, we have that the area of the triangle PQQ is equal to 8 times the area of the triangle PQR. Okay? Great. So that's the first fact we wanted to prove. And now we move to the next step. We want to count the triangles at each step in this process. And what I've done here is highlight what happens after this first step. So in the first step, we're looking at this larger triangle PQQ. But when we move to the next step, we treat our new parabolic segment as living here. And we identify a new vertex. This will be our P prime. And we just carry out the same analysis. And these red triangles will have area equal to 1/8 of the green triangles, of the green triangle. But we know that that's equal to, the green triangle has area equal to 1/8 of PQQ. So that means that this is 1/8 squared of the area of PQQ. Okay? So this is area of pink. Okay, well, how many pink triangles are there? We'll get 2 from this segment and 2 from the other segment. So there are 2 squared pink triangles. Okay, and the inductive argument, the induction is not hard to carry out, that there are 2 to the n triangles, since from each triangle in the previous step, you take a triangle on either side. and you'll get 2 to the n triangles of area 1/8 squared. Sorry, 1/8 to the n. Okay, so in terms of total area, move stuff around here a bit. In terms of the total area, we have 2 to the n over 8 to the n, which is 1/4 to the n. Okay, then if you want to add up all of these triangles, we'll get, so letting this term be a, okay, so let's call this a, we'll have a to start, plus 1/4 a, plus 1/4 squared a, etc. Okay? So this is justifying that we're approaching a geometric sum. Okay, and then there's just the question of how you actually add that all up. So for us, this is an easy exercise from the calculus sequence. This is given by 1 over 1 minus r, assuming that the absolute value of r is less than 1. Okay, so in our case, we have r equals 1/4. So that implies that the sum is equal to 1 over 1 minus 1/4. That's 1 over 3/4, which is 4/3. Okay, and that's why the area inside the parabolic segment is approaching 4/3 of the area of the original triangle. If you want a geometric argument, and this is one that appears in Archimedes' original formulation, so let's say you're looking at a square, and now you want to consider 1/4 of that square, and then, okay, so you're going to take 1/4 of that square and then 1/4 of the next square, and then 1/4 of the next square, and then 1/4 of the next square, etc. So when I'm talking about the sum 1 plus 1/4, or rather, let's just start with 1/4 since the 1 might confuse things. So you start with 1/4 plus 1/4 squared plus 1/4 cubed plus 1/4 to the 4th, etc., going up in this way. What you can see is that taking the shaded part, each shaded square has exactly two squares identical to it in this picture. So the sum of all the shaded squares must be equal to 1/3 of the total picture. So the sum equals 1/3 of the big square. Okay, but keeping in mind that we started with 1/4, so that means that if we just start with 1 plus 1/4 plus 1/4 squared, etc., this will be equal to 1 plus 1/3, okay, or 4/3. I thought this argument is nice, and it also reminds you of how little Archimedes was working with. Nothing was taken for granted. Okay, so let's go over this argument again. We start with the parabola. We cut out this triangle inside of it. And then we show that the triangles that you can build in the edges, their area shrinks in a predictable way. And then we can add up all of those areas, and it approaches 4/3 of the original area. But there's a subtlety here, because Archimedes didn't really have a theory of infinite series. So I cannot compute something like the sum of 1/4 to the n times a, where n goes from 0 to infinity. That's just not a thing that he did. So instead, he needed to make a more complicated argument. Okay, and that amounted to something like this. Let's consider the sum of the triangles at any finite step. Okay, so, or the union. Union of triangles up to an arbitrary finite set. This will be a lower bound on the area of the parabolic segment. Okay. So he didn't have the full ability to take a limit here, but by arguing about the finite steps in this process, he's still able to come to the conclusion that the parabolic segment has area 4/3 that of the triangle. Okay, so I think that's a pretty impressive feat of mathematics for ancient Greece. But perhaps a more famous one is Archimedes' measurement of a circle. Okay, so we know that the ratio of a circumference of a circle to its diameter is known as pi. And in his work, The Measurement of a Circle, Archimedes writes the following proposition: the ratio of the circumference of any circle to its diameter is less than 3 1/7, but greater than 3 10/71. Okay, it's a very small interval. The interval between those two numbers is of length 1/497, which is 0.0020. So it's very, very small. This is an excellent precision estimator for pi. Okay, so how does he get there? His idea is interesting. He uses inscribed polygons as well as circumscribed polygons. And the idea is that the perimeter of this is shorter than the circumference of the circle, and that the perimeter of this is longer than the circle. Okay, this first fact that it's shorter than the circle is not hard to see because the shortest distance between 2 points is a line, so the circular arcs are going to be longer than the lines in the inscribed polygon. The fact that the circumscribed polygon is longer than the circle is not a simple idea, and I've seen various attempts to explain how Archimedes came to this, but it seems to require heavier equipment. And he might have just taken it as an axiom. Okay, so in this case, we're looking at the hexagon. Okay, and the hexagon is a pretty easy to understand example because all of the constituent triangles are equilateral triangles. So we have 60 degrees, 60 degrees, 60 degrees. Okay, and we know that the length from the center of the circle to the circumference of the circle is given by the radius. So we're just going to take radius 1 for simplicity. So that means that the side here also has length 1. So the inscribed polygon has perimeter 6. Okay. Well, how about the outer circle. It's a little trickier. So we're going to need to use the fact that this length is 1. Okay, and we want to estimate this length. Okay, well, this bisects a 60-degree angle, so it's 30 degrees. So this is a 30, 60, 90 right triangle. So the ratio of the longer side to the shorter side of a 30, 60, 90 triangle is going to be square root of 3 to 1. So this can be written as 1 over the square root of 3. Okay, that's this distance. So one side of the hexagon will be given by 2 over the square root of 3. So the circumscribed perimeter is going to be 6 times 2 over square root of 3, or 12 over the square root of 3. Okay, and you have a factor of 3 in the top there, so this is 4 times the square root of 3. Okay, nice. And if we wanted to estimate pi, we would now use the fact that the inscribed perimeter has to be less than the circumference of the circle, which would be 2 pi, which would be less than 4 times the square root of 3. And this would give you an estimator for pi. If you want to use rational estimators, the square root of 3 here is not going to help you, so you can replace the square root of 3 by whichever rational number is useful here. And Archimedes had, from other sources or from computations he did elsewhere, that square root of 3 lives between these two rational numbers. Okay, but that doesn't give you the tight bounds that Archimedes had on pi. So how did Archimedes get from the hexagon to, which gives you this kind of weak interval for pi, to a much tighter bound? Well, he went from the hexagon to a 96-sided polygon by repeatedly doubling the sides. Okay, so in order to explain how he did this, let's think about, in general, what the formula for side of an inscribed n-gon or a circumscribed n-gon is. And this, is, by the way, is not how Archimedes did it, but the underlying trigonometry plays out in a similar way. So let's say we have a circle. Oops. Okay. And we're going to put the side of an n-gon, inscribed n-gon here. You know what, we'll use a different color. Okay, and circumscribed n-gon, let's put it here. Okay, and we're going to have the center of the circle here, and we're going to say, so it's because this is an n-gon, this so we have to divide 2 pi up into n pieces. So we have, this will be 2 pi, well, it's 2 pi into n pieces, so this full angle would be 2 pi over n, but then I'm just interested in half of that, so this will be 2 pi over 2n, so that tells me I'm looking at pi over n for this angle. Okay. So this point, as is well known to somebody who's studied trigonometry, this point has coordinates cosine pi over n sine pi over n. Okay? So in particular, if I'm looking at for the length of that green edge, well, I just need this coordinate, but this is going to simply be cosine pi over n minus sine pi over n. So that tells me that the side of the inscribed n-gon is going to be twice sine pi over n. Okay. As for the circumscribed n-gon, well, the value of the point here, the coordinates of the point here, are 1 minus tan pi over n, and up here it's 1 tan pi over n. So the side of the circumscribed n-gon is going to be twice tan pi over n. So we have this very nice description of I'm just going to move this a tad. We have this very nice description of our side lengths in terms of trig functions and the integer n. Okay. So now let's use that to figure out how long the sides will be and how long the perimeter will be. Well, actually, let's take a moment. So if the side of an inscribed n-gon is 2 sine pi over n, that means that the perimeter we'll just multiply that by n. So we have 2n sine pi over n. As for the circumscribed n-gon, that'll be 2n times the tangent of pi over n. Okay? So we can use that to define recursive formulae for the perimeter of an inscribed or circumscribed 2n-gon. So we're going to let an be the perimeter of the circumscribed regular n-gon, and bn will be the perimeter of the inscribed regular n-gon. And we'll use these trig formulae. For tan, we use the half angle, and for sine, we use, this should be sine of 2x. Which is a version of the double angle, right? It's just replacing cosine with sine over tan. So this is sine 2x equals 2 sine x cosine x. So, given that what we're interested in is a2n, okay, from the formula on the last page, that should be 4n tan pi over 2n. Okay, well that's tan pi over 2n. We can use this half angle formula to tell us that's the same as 4n times, and then on top we have tan pi over n sine pi over n divided by tan pi over n plus sine pi over n. Okay, well now we can multiply top and bottom of this fraction by 2n, and we have 2 times 2n tan pi over n, 2n sine pi over n, divided by 2n tan pi over n plus 2n sine pi over n. That tells me, well, at this point I can sub in what I know about an. That's the same as 2, an and bn, sorry. 2 times an bn divided by an plus bn. Okay? So that gives me a formula for a2n. If I want to know the perimeter of my circumscribed regular n-gon, I can get it in terms of the perimeters of the circumscribed and inscribed regular n-gon as opposed to 2n-gon. Okay, cool. So Let's add another page here. Now we want to compute b2n. So b2n is going to be equal to 4n sine pi over 2n. Okay. And we're going to use the fact that sine pi over 2n can be related to sine pi over n in this formula. So sine pi over n equals twice sine squared pi over 2n divided by tan pi over 2n. Okay. And now I can put together, so I want to group these sine and tan terms with factors of n so that I can translate them into the an and bn. So I'm going to multiply by 2n on both sides. So we have 2n sine pi over n equals 4n sine pi over 2n, and then sine pi over 2n over tan pi over 2n. Okay. So I'm going to move this over. Okay, well, 4n sine pi over 2n, so 2n sine pi over n, that's an. And then 4n sine pi over 2n is equal to b sub 2n. Okay, and then I can multiply top and bottom here by 4n, so we'll have 4n sine pi over 2n divided by 4n tan pi over 2n, and we'll get b2n, okay, and here again, oh sorry, that should be bn. bn equals b2n times b2n over a2n, okay, or in other words, b2n squared over an. Okay, and what that tells us, in particular, is that moving the an to the other side and taking a square root, we have b sub 2n equals the square root of an, sorry, this should be a2n, a2n bn. Okay, so now using an and bn, assuming we have it, and we do have that for n equals 6, right? We have 6 and 4 root 3. Using that, we can generate a2n and b2n with just these recursive formulae. And Archimedes had to do this with rational approximations, always making sure that he wasn't using the lower bound when he should be using the upper bound, etc. But we can do this just in a computer, hoping that we have pretty good accuracy. And we do this until we get the perimeters for the 96 gon, both inscribed and circumscribed. And what we get is that pi will be between 3.141,032 and 3.14271. So obviously we get the first three digits, 3.14, and that's pretty good. And it's pretty close to what Archimedes got, even though he had to frustrate himself working with rationals. So thinking about these amazing achievements of Archimedes in ancient Greece, we're looking at a kind of integration which is not really integration. So the method of exhaustion thematically works a lot like integration. You're breaking the region into smaller pieces and adding them up. But on a technical level, there are stark differences. So obviously at no point do we take a limit. And thinking about the case of the parabola, the triangles are finite and fixed at every stage. At no point do we say, okay, you're going to shrink all of your triangles simultaneously and try to take a limit, try to compute the limit of that. So that you're always computing the actual finite area of some actual polygonal region. So it's not quite all the way to integration, but it really does taste like it. And certainly the mathematicians who eventually developed the calculus knew Archimedes well, and his work was a major influence. Okay? And in the next lecture, we're going to see some other calculus-type calculations from other parts of the ancient world. Thanks so much for your attention.